So distributed systems are prone to problems that seems very obscure. GitHub had an outage because some nodes of a Zookeeper cluster ran an election and elected a second leader. I mean, how obscure is that? In this video, we dissect a GitHub outage that would tell us how weird the world of distributed systems is. We would also talk about how important Zookeeper is for managing a Kafka cluster. We would see what happened during the outage and how GitHub was able to mitigate it with zero data loss and a brilliant fallback strategy. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue. Instead, a small focused group of 50-60 engineers every cohort will be brainstorming systems and designing it together. This way, we build a solid system and learn from each other's experiences. The course to date is enrolled by 600 plus engineers spanning 9 cohorts and 10 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The coolest part about the course is the depth we go into and the breadth we cover. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale for any advertisement business. In all, we would cover roughly 28 questions and the detailed curriculum split week by week can be found on the course page which is linked in the description down below. So if you're looking to learn system design from the first principles, you will love this course. I have 2 offerings for you. The first one is the live cohort based course which you see on the left side and the second one is the recorded course which you can see on the right side. The live cohort based course happens every 2 months and it will go on for 8 weeks, while the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would highly recommend you going for the recorded one. Otherwise, the live cohort is where you can participate and discuss things live with me and the entire cohort and amplify your learnings. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass and I would highly recommend you to check that out. I put the link of the course in the description down below. So if you are interested to learn system design, go for it. Check out the link in the description down below and I hope to see you in my next cohort. So before we go to the incident report, let's spend some time understanding the importance of Zookeeper for a Kafka cluster. So Kafka is a very popular message stream. It has topics, it has partitions. Each topic can have multiple, or every topic can have multiple partitions. And Kafka is not a single node cluster. There would be multiple nodes that are running Kafka process. Right? And each node is called as a broker over here. Each partition of a particular topic has a leader and has a replica. Right? A broker can have a leader of one partition and a replica of another partition. Right? And this is how across such cluster, across this cluster, it is able to sustain a high read load and a high write load. So what Zookeeper does? Zookeeper fulfills four key responsibilities for Apache Kafka. First of all is controller election, basically the leader election. So here, for every partition, for every topic, there is a node which is acting as a leader, while other node is acting as a follower. Who does this leader election? Zookeeper. Who manages this information? Zookeeper. If leader goes down, someone else has to become a leader. Who does this? Zookeeper. Right? So Zookeeper is acting as a very nice brain that is doing this leader election for every topic, for every partition in the cluster. Second, it does cluster membership. So now that there are multiple machines on which your Kafka is running, you need to know which machine is in, which machine is out, whenever machine joins a cluster, whenever machine leaves the cluster, abrupt failures and whatnot. Who manages that? Zookeeper. Third is topic configuration. Kafka has multiple topics. Each topic has multiple partitions. Each partition, or a partition can be a leader or a replica. Where does this partition hold? Where should I forward the request to in order to send my data or in order to perform the writes or the reads? All of this information stored as part of topic configuration in Apache Kafka. Right? Then ACLs and quota, like who is allowed to read from a partition, who is allowed and how much is something which is managed by Zookeeper. So all of this information is stored in Zookeeper. So now here you see how important is Zookeeper for managing Apache Kafka. Right? So it is acting as a brain, as a ringmaster to hold and manage the entire cluster for us. Just a disclaimer, Kafka from version 2.8 does not have a true dependency on Zookeeper. Prior to that it had. Now they have managed, or they have built their own internal thing to manage the cluster. So they have removed the dependency on Zookeeper, but it still holds true. The concept, the outage still holds true. It might not be Zookeeper, it might be something else. Right? The foundations remain the same. Right. Okay. So now what we do is, now we take a look, now that we have a very solid foundation, we take a look at the incident report. So what incident report says: while reprovisioning Zookeeper nodes as part of routine upgrades, right? So every cluster needs to go through upgrades, and this is what we are talking about: Zookeeper nodes, not Kafka nodes, Zookeeper nodes. So while provisioning Zookeeper nodes as part of routine upgrades, new hosts were introduced too quickly, which resulted in the election of a second leader. Now let's spend some time understanding what exactly happened. So Zookeeper had a routine maintenance. Why do we need to do routine maintenance? Because version upgrade, OS patches, security patches, machine rotations, right? Normal routine process that was going on. So Zookeeper nodes were getting changed, right? And when this was happening, a lot of new nodes were added, right? And when nodes were added too quickly, what happened is they ran another election algorithm. So what happens internally, what happens whenever a node is added to a Zookeeper cluster, right? What would happen is Zookeeper is made to be near autonomous, right? So when a node is added to a Zookeeper cluster, what it would try to do, it would try to understand what the cluster looks like. It would try to understand, or it would try to do self-discovery on how it fits into the cluster. Right? When a lot of new nodes were added into the cluster, they could not find a leader, or they could not discover a leader. Might be any reason. They could not discover a leader, and the majority of information that they found was like they seem to have majority of nodes not knowing where the leader is. Right? And this is all written in code. This is not some hypothetical thing that I'm talking about. This is all written in code as part of the bootstrap code of any true distributed system. So when a lot of nodes are added, these nodes did not know where, or they were not able to quickly discover the leader. So then what they did, they triggered a leader election, right? And this is where what happened is, and because there were too many nodes added too quickly, leader election was successful. They were able to elect a new leader. The old leader was there. They elected a new leader. And the newer set of replica, or the newer set of nodes became part of a second logical cluster. It was not a physical cluster. They were all part of this one cluster. But within that, they elected another leader. So the end state of this, after they added nodes too quickly, was that they had two logical clusters with two leaders and multiple replicas. And this is, I'm talking about Zookeeper cluster, right? So now we have two logical Zookeeper clusters part of the same infrastructure, right? Okay. So now what happened? And this is not so common, but a distributed system will have this problem sometime in the future. Like it would bound to happen. Basically, a second leader problem or a second brain problem is bound to happen, right? So this happened for Zookeeper. It happened because we added the GitHub team added a lot of nodes in a very short time, right? So leader election had to spun up. And why I said had to, because the nodes could not discover an existing leader quickly. Right? Not so common, but very possible situation, right? Okay. So then what happened? So after they added this, effectively introducing a logically distinct second Zookeeper cluster where there should have been only one. So now how they are operating is, now we have two logical Zookeeper cluster, right? Now depending on where anyone connects to, it would be part of that cluster, correct? So that's exactly what happened. While the Zookeeper hosts were in this state, a single Kafka broker in the cluster connected to the newly formed second Zookeeper cluster and elected itself as the node controller. Okay, brilliant. So what happened? There were a lot of brokers who were connected to old leader, or they had information about old leader and old followers of Zookeeper, right? A single broker got added or got connected to this new logical Zookeeper cluster. And when it got connected to this Zookeeper cluster, now this broker just spun up, and this broker is also autonomous. The bootstrap code of this broker would be what? Hey, for this topic, is there any leader? It would check in the Zookeeper cluster. In the Zookeeper cluster, this cluster does not know the existence of other cluster, right? So this cluster would say, no, there is no leader for this topic. This broker said, hey, I would be the leader. And this is exactly what happens with a split brain problem. So when this broker got connected to this newly formed Zookeeper, it elected itself as the controller for a particular topic. So now what happened? Now this could be for a topic, for multiple, they have not specified it, but it elected itself as a controller. So now you would have multiple controllers in your Zookeeper in your Kafka cluster for a same set of topics. Problem. So now what would happen? We already had two distinct logical Zookeeper clusters. Now we are having two brokers claiming to be a controller. Now what would happen? When clients connect to, when basically clients are connecting to Zookeeper to get the information. So whenever a write needs to happen to Kafka, let's say you're writing it to the Kafka, you have to talk to Zookeeper to get the information on where to write, on to which node do you want to write, right? So when they connect to Zookeeper, what they're getting is they're getting conflicting information. So client, it would require some time for the client to discover that they are getting conflicting state of information as part of response from Zookeeper. Now, how would they do it? When you make a call to Zookeeper cluster and get the information, the Zookeeper internally fans it out, grabs it, and then basically returns it to the client. Okay, hey, this is the consistent view of the information, right? In order to get that consistent view of the information, it would have to talk to a lot of stuff, right? When it does that, what would happen is the client is getting conflicting information. As our client is getting conflicting information, it would drop the writes, right? It would not proceed further because it knows that something's wrong, right? So the writes would start to fail. There might be some writes, and this did not happen with GitHub, but there might be some writes that would have gone to the from the new broker to the new Zookeeper cluster. It would have told some broker's IP and it would have gone to that. But here only one broker was added, right? That's why GitHub became lucky. Only one broker got added to this new cluster. So there was not data loss. But if there were multiple brokers and they themselves elected themselves, hey, I'll be the follower, you be the leader and all. If that would have happened, then the writes would have been successful in that, right? But for some time duration, until Zookeeper heals itself, there would be a state where your cluster is sending inconsistent information. And while it is sending that inconsistent information, what would happen is your writes would start to fail. And that's what happened. So here what happened, at this point, there were two distinct Kafka clusters that were serving conflicting cluster state information to the client. This incorrect state caused write failures to approximately 10% of request to our background job service, resulting in backup of jobs. We'll talk about this. So here what we clearly see is there were two distinct Kafka clusters that were serving conflicting cluster state information to client. This is where your client needs to be smart enough to understand that I'm getting a conflicting set of information, so I should not be writing to this, right? In most cases, you have to handle this, right? So what happened over here? How did they even recover? So there are two ways to do it. Zookeeper does a periodic, cleanup, not really a cleanup, but basically a periodic heal if it requires to do so. So Zookeeper can auto detect this inconsistency over time, and it can auto heal, quite possible, right? But it takes some time to do this. So instead, if you don't want to wait for that long, you can manually take actions to fix it. For example, killing the second logical cluster. And how would you know that there is a second logical cluster? Zookeeper configuration. Because your writes are failing, you would have gotten a PagerDuty alert. You would see in the Zookeeper configuration, you can totally see the two leaders are getting elected. or 2 leaders are operating, because of which the writes are failing, you would be deleting those entries from Zookeeper, right? And removing those nodes, right? This is how the recovery would happen. Wait for the auto heal to happen, or otherwise take manual actions to fix it, right? So with this sort of recovery strategy, what exactly happened? What did GitHub do? There was some very fancy things that GitHub was talking about. So the incorrect state caused write failure to approximately 10% of the request to our background job service, resulting in backup jobs as we migrated traffic and worker capacity to our secondary job processing system. Two keywords, 10% request fail and secondary job processing system. So what typically happens? So what got affected over here is their internal background jobs processing system, right? Some internal jobs that they were running, they stopped processing because writes were failing and whatnot. So did they lose? Like, this looks like a pure case of data loss, because the writes was supposed to happen, but writes failed. So why wasn't there a data loss? This is where a concept of fallback queues come in. So whenever you are putting a message in a broker, what you should be always doing is, if writing that message to a broker fails, have a provision of something called as a dead letter queue. It's a very standard nomenclature. So dead letter queue is what would hold the messages that got failed. So if your client is writing to a message to Kafka, and if this fails due to some reason, it would write the message to a dead letter queue. It has to be a very cheap queue, mostly a message broker, not a message stream. But what would you do? If your client tries to write to Kafka, it does with some retries, 3 or 4 retries, and if it still is not successful, it would write it to a dead letter queue. This becomes your secondary job processing system, right? Your primary one is where you ingest it into Kafka and there are workers consuming it. But in case your write to the Kafka fails, have a fallback. And this dead letter queue is a fallback to do so, right? So this is what came in very handy. Because of this, there was no background jobs were lost during this incident. Why? And while we experience significant queue backups for some systems, the retry behavior in our clients and presence of redundant queuing system mitigated such issues. Right? This clearly shows the importance of having a secondary job system or a secondary job processing system. So your client was writing to Kafka, it failed, it pushed to dead letter queue, right? So there is no message loss whatsoever, right? And there are consumers. These are the primary consumers which are reading from Kafka that did not get any job because writes were failing. So your dead letter queue, consumer started processing it. So there was no data loss. But what would happen is, because this is not as throughputy as Kafka, a lot of things would pile up, right? So it would take some delay, but no data loss. Very important, right? Delay is okay for internal job processing system, but not data loss. So this is a very key design thing, or this is a very key design that you all should remember, that having a fallback strategy is very, very, very important for every single thing. Like here, you cannot assume that Kafka is always working. It can also fail. So have a dead letter queue, right? Okay, so some important key takeaways to conclude this discussion. First of all, having a dead letter queue is a must. So if you are relying only on a single queue, don't do that. What if that queue goes down? What if that broker goes down, right? Have a dead letter queue so that you have a secondary job processing system so that you don't have any data loss, right? Second point is consumer should be idempotent, right? It's very important that your consumers, the way you are writing your consumers for any job, for any message processing system, the consumer that you are writing has to be idempotent in nature. If it is not idempotent, then your data would become inconsistent. Ensure that it is idempotent. Third, your clients and consumers should have retries, right? Your client should not just make one call to Kafka and expect it to write. There should be retries. After 3 or 4 retries with exponential backoff, you can say, hey, now I'm unable to write to the Kafka. Let me put it to the data queue. So give yourself or give your client a chance to write. Or if there are any transient issues, it would your eventual write would succeed. But if that fails after 3 or 4 retries, you put it into a DL queue, right? And the fourth one, automate cluster provisioning with a jitter. So here what happened, when GitHub tried to do it, or when GitHub was adding node to Zookeeper, they might have done it manually, because the last paragraph of the outage says, to avoid this class of failures in the future, we have updated our Zookeeper provisioning checklist and plan on introducing automation to perform Zookeeper and Kafka cluster maintenance. So this shows that it is quite possible that some engineer would have added more nodes into Zookeeper cluster, or was doing manual rotation of Zookeeper cluster, in which he or she added a lot of nodes in a very short time, which led to this. Pure speculation, not the person, or I don't have any insider information. Pure speculation. But in any case, specifically with distributed systems, you have to take your time, right? And whenever you are adding or scaling up your infrastructure, add a jitter. Every single cloud provider gives you that ability. If you are doing manual provisioning, add a jitter explicitly. Don't do it like add 50 nodes in one shot, right? Never do that. Add some jitter, add some random delay, and then you add nodes slowly and steadily into the cluster, right? 4 key important learnings from this particular outage. Nice. So yeah, that's it. That's it for this one. I hope I made sense. It is very confusing, to be really honest. Distributed systems are meant to be like this, but something that you cannot definitely run away from. It's the beauty of the distributed systems in any case. Nice. So yeah, that's it for this one. If you guys like this video, give this video a thumbs up. If you guys like the channel, give this channel a sub. I post 3 in-depth engineering videos every week, and I'll see you in the next one. Thanks a ton.